leader of the machine learning team at INS and the leader in the fields of optimization and machine learning in the world. He was awarded many awards during his career. For instance, he was awarded the ICML Test of Time Award in 2014, the Lagrange Prize in Continuous Optimization in 2018, and the Jean-Jacques Moreau Prize in 2019. In 2020, he was elected in the French Academy of Sciences. And so we are very pleased to have him here and looking forward to his talk.
Okay, so thank you, Soledad, for the invitation and the very generous introduction. So today I will talk about joint work with Lénaïque Chiza, okay, with a researcher at Orsay. And let's jump right to it. So the idea today is to look at supervised learning and to study the classical situation where you have some observations xi, yi. So xi can be an image, yi can be a label. And want to predict a new y given some x through some prediction function h of x and theta. X is the input and theta is the parameter, so very classical. And the idea is to, we have two types of models that people care about in machine learning. You have linear models, where you have a linear function of the parameter theta. It could be nonlinear in the input x through some feature of map phi of x. But this works a lot for many instances, for example, for advertising, where phi of x is very large. But more and more, you tend to see neural networks appearing for problems which are like beyond the capabilities of linear models. And this is a classical example from computer vision, where you end up with a sequence of linearity, theta1 transpose x, plus some nonlinearity taken component-wise, and you iterate. And you get a neural network, which is deep if you have many layers, which can be convolutional if you want to do computer vision, can have pooling, a lot of things that can be put on top of it. But the core difficulty for us is that it's a nonlinear function of the parameters, and this leads to, as I will show, non-convex problems. So how is it learned? Typically, you minimize some data fitting term, which is the average of some loss. And in this talk, I would assume the loss is convex in the second variable, so convex in H, which is a weak assumption. So logistic, cross entropy, least squares, they all satisfy that. And I'm going to add sometimes a regularizer to avoid overfitting. So this is a classical empirical risk minimization framework. And just as I'm going to use it later in the talk, this is just a mean to an end. Okay, what you really care about is to do well on unseen data. Okay, so this is important for machine learning. So learning is not simply optimization, this is also generalization, and I will come back to that later in the talk. So I've mentioned convexity. So if your prediction function is convex, is linear, and the loss is convex, then you get a nice convex optimization problem. And this has very nice consequences because you have lots of algorithms for which you can have like quantitative runtime and prediction guarantees. Okay, so you can do stochastic gradient, variance reduction, and so on. And this has led to what I call golden years of convexity in machine learning, where many techniques were derived and in many areas. So I'm mentioning a few here, but there are many others. And for which you had like a significant match between what you could show and what you would see in practice. So this is like still going on. So this is not ending in 2020, but what we would like to know is whether we can do this for non-convex optimization problems, namely for neural networks. Okay, so the goal of the talk is to see if we can go as far as for convex problems, and the answer will be not yet. So let's go to it. So the goal is to have some study some multi-layer neural network, and I'm going to simplify as a with respect to computer vision. I'm just going to take a fully connected network and here two hidden layers, and this is not what is used in practice, but this is already difficult enough for us. So for this, there are two main difficulties I'm going to study today. The first one is optimization. So we end up with a non-convex problem. So can we solve it reasonably well? And second difficulty, typically when you have lots of neurons, and this is often called the over-parameterized regime, where the number of hidden neurons tend to be large, then you may have some generalization issue And I'm going to see if we can generalize correctly. All right, so first optimization. So as soon as you go non-convex, weird things start to happen. So it's a function in 2D, okay, with level sets in color. So you can have like one global minimum, a few local minima, global maxima, saddle point, and so on. And so you have to be careful with those functions. So the first thing that people have tried is, if you can't go global, why not go local? And there's a very nice series of works. Some of them are cited there, where people show that all the classical gradient-based techniques, sometimes by adding some noise, will converge to either a local minimum or a stationary point. And if you add some noise, typically you can escape the stationary points. So this is all very nice. This gives you like convergence guarantees, but still to a local point. And nobody can tell you if you're local or global. Then you may say, why not going global? Okay, so the first bad news is that it's impossible to go global without exponential dependence in dimension. And this is a classical like function which is very hard to optimize, which is flat except at a given area. And unless you sample by chance some point in this region, you will never be able to find the global optimum with local information. And of course, in 1D, it's easy, but the volume of this will shrink to 0 with dimension very quickly if you let the dimension go up. Okay, so this is impossible to get like global guarantees for all non-convex problems. So this is very well known. But then you will tell me, who cares about those functions? Okay, not very interesting. So let's try to focus on functions that we care about. Let's reduce the scope, not all non-convex, just the non-convex functions which I care about. And let's look at that. And what we care about at the moment is deep neural nets. And there's those first series of work looking at that, and there are many others now, of course. The first one is to look at models for which local minima are in fact not a problem. Okay, so this can be done either through some random models by Chomsky and colleagues, or by assuming some specific activation functions. Okay, so you reduce the scope a bit compared to neural nets by adding extra assumptions, and you can get some interesting results. What I want to tackle today is the classical neural network that you use in practice, like ReLU type networks. So let's look at that. So I'm going to simplify things even more. So I will stop there, okay, in terms of simplification, and by looking at the first non-trivial nonlinear model. So a single hidden layer, or sometimes people call this a two-layer neural network. When you have inputs X over there, then you have your input weights, θ1, it's a matrix because X is a vector and you have like more than one hidden neuron. So θ1 is the matrix of size, number of inputs, number of hidden neurons. And θ2 is a vector, the output weight, because I'm assuming a single output function. So this is a neural net over there. And you can see it like through the formula over there, where you see the input weights as a matrix here, and here θ2 at the output weight with a vector. So why do we focus only on a single hidden layer? For a very simple reason is that we are going to need a lot that our prediction function H is a sum of prediction functions which have their own parameters, and those parameters should not be shared with any of the other elements of the sum. Okay, so it's like independent parameterization, and which is so here Wj will be the set. You take a neuron, so J will be an index over the hidden neurons. Okay, and you put in Wj both the input weights that are going from the inputs to that neuron and the output weight. Okay, so both θ2 of J and θ1, like the J's column of θ1. And so here, with a single hidden layer, it's easy. There is no sharing, okay? And I'm going to leverage this a lot in this talk. If you go to more than 2 hidden layers, or 2 or more, then you start to have sharing. And this is, in fact, the goal, one of the goals of neural networks. And this, whatever I'm going to say today, does not apply to that case. So there's still like open problems in this area a lot. Today, 1 hidden layer. The goal will still be to minimize some risk, which is an expectation over some distribution. That could be sometimes the empirical, sometimes the test distribution of the loss between y and our prediction function. And I'm going to assume R is convex. Okay, so as I've mentioned, this is just the loss is convex. So I will consider this as an OK assumption. So the problem is not convex because psi here is not linear. Okay, you have the sigma over there. So in this talk, I will sometimes consider sigma as being the sigmoid, or sometimes so-called ReLU as the positive part, depending on the context. All right, so let's look at this. So the main insight that I'm going to leverage, so it's not our insight, it's very classical insight in signal processing, statistics, and machine learning, is if I go to an over-parameterized model where number m will start to grow, then I can see my average of functions as the integral over some probability measure, and I get equality if I use the empirical distribution of my neurons. Okay, and the idea is that when the number of neurons go to infinity, then we converge to a so-called mean field limit, where we can replace the set of Diracs by density. Okay, so it is essentially what I'm going to do, is to see the limit when the number of neurons go to infinity, the limit of as a density. So this is a classical idea that's been used like quite a lot in statistics and signal processing, and we're going to use this. The first effect is that we have, in a sense, linearized the problem, because our H, which was like parameterized non-linearly in WJs, is now parameterized linearly in the measure. Okay, and so we have a convex function, we have a linear parameterization, so we have made the problem convex. Okay, so it's convex, but the issue is that it's convex over measures which are infinite dimensional. So you have made the problem convex, but it's not really useful. And the first thing that you can think of is it's convex on a set of measures. So measures are the convex hull of Diracs. So maybe I can use like Frank-Wolf techniques, which are dedicated to learn over convex hulls. And this people have tried, but the issue is that the task of adding a neuron to the convex hull to do incremental learning, which is like classical for Frank-Wolf techniques. So the task of adding a new neuron ends up being like NP-hard. Okay, so you replace a difficult problem by a sequence of difficult problems. So it's not really helpful. And even more importantly, nobody does that in practice. Okay, in practice, what people do, gradient descent. So let's try to study what people do. Okay, and they don't really go to the mean field limit. They just take n being very big, okay, and just do gradient descent. Okay, so let's try to study what gradient descent is doing. So maybe 3 questions, and we will partially answer today. First, what is the algorithmic limit when m goes to infinity? Does it mean something to let m go to infinity mathematically? Then once we have a limit, does it behave correctly? First, in terms of optimization, so we'll show global convergence to some global minimizer, and in terms of performance, how does it perform when you have an infinite number of neurons? All right. So the first part is this joint work with Enek Shiza again from 2 years ago, where again we just minimize the function of a measure, which is a convex loss R, convex risk, over some linear combination, and we're going to minimize classically through the neurons themselves. So we're going to not study gradient descent or Sgd because it's too complicated for us. So we instead look at the gradient flow. Okay, so we are going to simplify the problem even more. And the idea is that having a gradient flow converging is the first step towards having like actual algorithms converge. And you see what I call the idealization of Sgd or GD. The idea being that when you study single pass Sgd, then in fact in the early days of Sgd, this was studied through like a link to the gradient flow. Okay, so in Sgd, if the step size goes to 0, then it follows the gradient flow, okay, of the test risk if you do a single pass. And if you do a multiple pass Sgd, so you also follow the gradient flow, but now more of the empirical risk and not of the testing risk. Okay, so it's just like classical thing for Sgd. If you do a single pass, you won't overfit. If you do multiple passes, you may overfit. I will come back to that later on. All right, so now we're doing gradient flow. And so the first question is, what does it tend to when m goes to infinity, m being the number of neurons here, hidden neurons. And this has a name. As a name, it's called a Wasserstein gradient flow. So it's a particular geometry over the set of measures based on the optimal transport. And here, details do not really matter. It has a limit, which is well defined. And in terms of density, you obtain a PDE on the density, which is classical in the Wasserstein gradient flow. And if you want to know more, there's a lot of nice papers doing this. Okay, and in this talk, I'm just going to assume that it has a limit, and the limit is an object which is well defined, and I'm going to study this limit. Okay, so this is a key part here. We take m infinity and study that object. All right. And so what can we say about global convergence? And so this is the first informal theorem. And so I say informal because there are a lot of technical assumptions. This is quite strikingly different from the convex world. So in the convex world, you would come up with some super simple assumptions like regularity, and then you will get, like, after t iterations, it goes as fast. Here, we are very far away from that. This is simply when the number of particles go to infinity, and I don't know how big m needs to be, then the gradient flow will converge to the global optimum, but I don't know the speed at which it will converge. Okay, the only non-trivial part in this statement is a global optimum aspect. Okay, so there is that this can be made more precise and with a clear statement with like some technical conditions, like regularity conditions, and you can look at the paper for that. But I would just mention two key ingredients: homogeneity and initialization. Okay, so this does not work for all problems. You have to have something which is particular to neural networks, and let's study that. The first one is homogeneity, and this was used also by work by René, you need your C of W, your atoms, which are combining linearly, to exhibit some form of homogeneity. So for neural networks, you're always homogeneous with respect to the second layer. So if you multiply θ2 by 2, you multiply psi by 2. Okay, and if you use like the ReLU, you are even globally homogeneous. So if sigma is a positive part, if you multiply θ1 and θ2 by 2, you multiply psi by 4, so you're too homogeneous. And so this can be leveraged. This is important. So our results are not true if you're not, if you don't have homogeneity. Okay, there are counterexamples, very simple ones if you don't assume homogeneity. So first condition, we have to have something special about the problem. And second condition, you have to initialize correctly. This is important because in the Wasserstein world, you can get stuck with the gradient flow. Okay, so this is well known for people doing neural networks. Okay, so when you launch a neural network and you do gradient descent, you may get stuck. Okay, and so it's a problem where there are stationary points. There are like many weird things. So you need to initialize correctly for this to be true. And here we just initialize in the way people are initializing those neural networks nowadays, which is just like random. Okay, so uniformly at random, and you need to cover all directions. Okay, so this is important for the algorithm to be true. Technically, we're going to assume that we have a density which covers all directions. So we have to initialize with a density over all directions. Okay, so this is the result. So let me emphasize on the fact that this is only qualitative. Okay, so I will not tell you a big M needs to be, and I cannot tell you how fast I will converge. Okay, those are still open problems. All right, so just like a simple simulation to illustrate the results. So this is a problem in 2D, okay, where I have I'm generating the data from a neural network like that. Okay, I'm using a square loss, and then if I minimize the square loss, the global optimum will be with 0 error. Okay, and here, because I'm using the ReLU, here I'm plotting here the directions of those elements. So those are, if you are in 2D, those are elements in 2D. Okay, so I'm recovering the correct neural network if I align with the generating directions. So in the dotted here, this is the optimal positions, and in the small like dots are my neurons, my hidden neurons, which are moving in that space. And what our result is suggesting is that if I have lots of neurons like this, okay, in the right, 100, then they should all converge to the true neurons. So this is what we more or less show. I say more or less because we know that if you replace 100 by infinity, it's true. When you do 5, you get stuck in local minima. And what is surprising and still like a subject of intense work, but with no success so far, is if you're a bit intermediate, okay, we know that with 5 neurons, it's enough to get to the global optimum. With 5 neurons, we often get stuck, but with 10, we typically don't get stuck. Okay, so here we generate data randomly, uniformly, and so on. So this is a width of the open problem. M does not need to be infinity for this to show, for this nice behavior to show, but we don't know exactly how big M needs to be. So then you can look at small video of the neurons just to highlight the fact that, and of course I didn't, okay, I didn't check before, so no video, sorry. Let me just do this quickly. Okay. Okay, let me share again quickly. Sorry, pop up. Et voilà. The video should be there. No? No? The video has disappeared. Okay, no video. Sorry. Okay, sorry about that. Should have checked before. All right, so I had a video, but no video. And then summary. Yeah, so now I have a result showing that I can optimize correctly. Okay. The question is, where does it tend to? Okay. So this is a summary that what we have seen so far. With if you have a model of that form, like an average of models, okay, then if the number of neurons goes to infinity, then the gradient flow converges to the global minimizer of the risk. Okay. So this requires a well-spread initialization. And at the moment, there are no quantitative results. So what we have seen as well is that if you do single pass Sgd, okay, then here, this is the test risk that you have. And we know that if you have access to sufficiently many data points, then you will converge to a good location. But typically, it tends to underfit. Okay, so nobody does single pass Sgd in practice. People tend to do multiple passes. If you do multiple passes, then you have to be careful because you may start to overfit. Okay, you should converge to often like 0 training error. The question is, it should overfit, and does it overfit? Okay, so this is essentially the question I'm going to tackle now. If I run full random descent, the random flow to the optimum, does it converge? Yes, René?
Quick question.
Yeah.
Do the summary, the main result, have any assumptions on the loss function and whether there is also any regularization or is just without regularization?
So here, this is, no, the loss has to be convex and there is no regularizer. If you can, you may add some regularizer, and to let me, have not succeeded to start again the video. Okay. Can you still see my screen?
Yes, we can.
Okay.
Not in full
yes,
mode.
So here you may add some regularizer over there. That's totally fine. You need to converge to the regularized risk, because the regularizer is also of that form. It's a linear function of an expectation. So you add linearity on top of convexity, so it's fine. What you need is that the R is convex, okay? And so if you add linear part, it's okay. And so as long as you regularize if you regularize independently over each neuron, is fine. If you start to use like trace norm type regularization, this may not be true. I don't know, but it may not be of the form of an expectation.
Okay, thanks.
And yeah, and so again, so I've mentioned that if you start to minimize a very flexible model. Okay, so neural net with many neurons. As soon as the number of parameters gets bigger than the number of observations, okay, you will probably end up in a full interpolation. So if you use square loss, you end up with your h of xi being exactly yi, and in general, you're going to get to zero loss. Okay, so this is a classical. This can be used for optimization. Okay, some things over there. But the key question is, for us, we know that we're going to end up in zero loss, but there are many H's with zero loss, and which is the one we converge to. Okay, so it's often called the implicit bias of gradient descent. We end up to zero loss, but some predictors with zero loss are very bad, some are very good. And can we say something about the one we converge to? So what has been shown by like a nice group of people like Surya Gunaseka and Sudri, Blake Woodworth, Sati Sebro, and other colleagues is that typically, if you run Sgd, you end up to a minimum Euclidean norm solution. Okay, so if you learn on a finite dimensional space, you end up to the minimum norm solution. The funny part is that it's difficult to show for the square loss. It's not even true. But if you do the logistic loss, then it becomes relatively easy. At least after you read those papers, it becomes relatively easy. And this is what I'm going to present now. So here, this is just like a detour through linear models. This is essentially the work of Gunaseka and colleagues. So it's logistic regression. Okay,
wait, we are not seeing your slides change at this point.
Oh,
are you changing your slides?
Yes, I am. So let me.
Yes. Just now we see the maximum margin and logistic regression. Maybe you want to put it in full screen? Or maybe...
Okay, let me. Let me do my thing. But I know a fix. I know a fix. This video thing. I'm trying to correct it. Yep. Good now.
Yes.
Okay. Yeah. So this is a detour through plain old logistic regression. Okay. So this is just linear models. Okay. Very classical. And I'm going to assume separable data. The idea being that in the high dimensions, typically you have enough modeling power to get to full separation. So there is the data so that all the margins are aligned with the labels. It's bigger than zero. And by just, if you have zero, then by rescaling, you can get one. Okay, so it's a traditional like separable data assumption. And what you can show is that when you run like binary classification, okay, then if you were to use a hinge loss, then this would be the SVM, the classical like max margin SVM. But when you use a logistic loss in green over there, then if you want to get to zero loss, you have to go towards large value of yi times this. Okay, this means that the global optimum is attained at infinity. And this is this could be a bug. It's a nice thing to ask your student to run gradient descent and logistic with separable data. Often you see like some angry emails afterwards because it's diverging. And so it's not a bug, it's a feature. And this is the work of Sudri and colleague. And what they showed is that it does diverge, okay, because the global optimum, there's no minimum, okay? So it's one of those situations where the infimum is zero, but it's never attained. So gradient descent will diverge, but if you look at the direction of divergence, then it does converge to the maximum margin separator. And this is like a figure taken back from the 90s, okay? And this is a maximum margin SVM, so minimize square norms such that you fully separate the data. And so essentially what they showed is that running gradient descent will converge like after rescaling to the maximum margin SVM. Okay? So this is a very nice result by Sudri and colleagues. Now the question is, how do we extend this to neural networks? Okay, because this is just linear models. So let's try to extend it for the remaining like 10 minutes. All right, so let's look at logistic regression for the two-layer neural network over there. So we have output weights, input weights, and we're considering the other parameterized regime when m goes to infinity. And we will exhibit two different regimes. This is also joint work with Plenary from this year. And depending whether you optimize only the output layer or only the input, the two layers, you get something different. Essentially, as you should expect, we're going to converge to some minimum norm thing. And the goal of the rest of the talk is to define what are the norms we're going to converge to for those two problems. So for the first one, it's going to be a kernel, which is to be expected because we only optimize about the linear part of the model. And the harder one is when you optimize about the two layers. So let's first look at the kernel regime. So we have here, we optimize over only the output weights, and those weights are random and fixed. And because we only have optimized over theta2, it's the linear model, okay, with a feature vector, which is this one. Okay, we have a big feature vector, okay, and with theta1 being random and fixed. So now a minimum N2 norm in linear models, we know what this is doing. This is converging to the minimum Euclidean norm and for theta2. And we know that if you penalize the Euclidean norm with linear models, there is a link with kernel methods. Okay, and essentially, this link is through the kernel function. So if you have a linear model with featured sphere of X, at the end, a quantity of interest is a kernel, the dot product between two feature vectors. And when your feature vectors are of that form over there, the dot product is an average over all of your input weights. So this average, when m goes to infinity, converges to an expectation, just a law of large numbers. And this is a so-called random feature model from Radford-Neal in 95 and Raimi and Recht in 2007. So essentially, when m goes to infinity, we know exactly where we converge to. We converge to a kernel method. Okay, and the good thing about kernel method is that the norm that it does on the space of functions is well defined. It's called a reproducing kernel Hilbert space, and you end up with smooth functions. Okay, this is often like a very counterintuitive element. We end up combining a lot of non-smooth functions, but because you combine infinitely many, at the end you get a smooth function. Okay, so you can only get a smooth function if you do a kernel method. And what is the informal theory that we have? Again, you can look at the paper to get more detail. That if m goes to infinity and you only optimize over the output weights, the kernel flow converges to the function which is minimizing the RKHS norm. Okay, to get the smoothest separator. So because it's convex here in theta2, you can get some quantitative analysis. It's one instance of double descent, so we can maybe talk about this during the question Q&A session. But one important part is this is a totally useless result in practice. Why? Because as soon as the number of neurons is beyond the number of observations, you don't need to use a random feature model. You can use directly the kernel. Okay, so this result and that setup has no practical significance because there are better ways of optimizing that model. Okay, it's just to highlight the fact that when m goes to infinity, something's happening. Now let's go to the interesting part. Okay, what's happening when you optimize over the two set of neurons? And for this, I have to do a detour on the RKHS part to understand what it means, this RKHS norm. And this can be seen, the norm, so the norm I just defined earlier is you represent f as the linear combination of your like Rayleigh functions, okay, with a with some a's density, and you penalize the N2 norm. Okay, so this is essentially you do an N2 norm penalization, and you only get smooth functions. What you're going to end up doing when you do like optimizing over the two layers is in fact the L1 norm. So the only thing that is changing here is that the 2 has become a 1, okay, and then you start to obtain the classical L1 norm effects. You're going to converge to, you're going to get sparsity, okay, so here, this means that you're going to allow the measure A times d tau to be singular, okay, so you can really select a small number of neurons, and when you have a small number of neurons, you can get to very non-smooth functions, so it's a much richer space of function. It's going to adapt to specific properties. So if, for example, your function f, the target function only depends on the subspace, you will find it. This is a sparsity effect. And this is essentially what's happening. You're going to learn features which are adapted to your problem by moving the input layers. When you just sample the input layers and never change the input layer, you're not going to get to any adaptation. It's essentially what we have shown. Okay, so if you optimize over all weights, then you end up with a minimum norm separator. This is to be expected from the setup. You do gradient descent, but the minimum norm, the norm that you obtain is specific. It's a variation norm, where you do learn representations. Okay, you do adapt the features to your problem. You get some adaptivity to linear structure. You can look at the paper if you want to know more. And the funny part is that for that problem, I don't know of any polynomial time algorithm from the convex world. Okay, so where the norm is convex. So the minimum norm interpolator, it's a convex problem, but we don't know how to represent the norm in finite time. The thing that we know is through particles, by sampling. Okay, but what we still don't know is the number, how big M needs to be. Okay, so we have the same problem as before. We take M very large, but we cannot tell you how big M needs to be. Again, for the experts, it's just the end of the double descent curve. Okay, showing that although M is infinity, you convert to a place which is not, reasonable. It's just a minimum norm interpolator. Let's look at this, but now really I need the video. So let me do something. 30 seconds. 30 seconds. It should work. If it doesn't work, then I'll give up. But so let me open a new other one. If it works, I will have deserved my apéro later today. But I'm skeptical. Okay. No, doesn't work. Okay, I lost my apéro. No, no apéro for me. All right, so what I was about to show was like a plot between maybe videos are disabled, maybe, I don't know. Anyway, so what I was going to show is like a plot of different parameters. Okay, so what you won't see today, and let me skip directly to the comparison of the various regimes in terms of test performance. Okay, so here what we do, we simply take like very simple data. So the first two dimensions are like classification which are separable. We add some nose directions. Okay, we compare kernel method, which is just training the output layer, or plain neural networks, where you optimize over the both layers. And the test error, as you can see, goes down quicker for neural nets because you identify the correct dimensions. You have the L1 effect, which is appearing there, whereas for the orange curve, you have two layers. You only optimize over one layer, and hence you don't get adaptivity, and you get to be perturbed by the 15 noisy dimensions. Okay, it's just a way to highlight the fact that you have some adaptivity to linear structures. So to conclude on this or summary, so I presented a qualitative analysis of gradient descent for two-layer neural networks. So the key two aspects were first, a global convergence if you have infinitely many neurons. And second, what you converge to is a maximum margin separator if you have like binary classification. And the idea is to converge to minimum norm, and we are defining the norm which you obtain in that setup. So big caveat, it's only qualitative. Okay, so I wish I knew more, but it's not the case. So this leads, of course, to obvious open problems. How do you make this quantitative, both in terms of neurons M and time T? Okay, so those two aspects, we are totally clueless at the moment. Of course, this is just like a single hidden layer neural net with fully connected. So nobody really cares about that. What you care about is doing a bit of convolutions and doing a bit of deeper network, but this is still totally open. On this, I will thank you for your attention. I'm sorry about the video problems, and I'm happy to take questions.
Thank you, Francis, for the very nice talk. Maybe you can show us the videos in the Q&A session.
I know. I have the video. I have the video.
Okay.
I never give up. I never give up. And I think I found the mistakes. No, I want my apéro. I want to deserve it. And I'll show the video. This one's going to work. I know. I know. Are you ready?
Oh, wow.
Yeah. Okay, so this is the neurons moving. Okay, so let me take 1 minute to describe the video. So this is in 2D, and we plot the neurons over the left. Okay, the way they move in their 3D space. Because 3D because you have a bias term. And this is how the predictor is moving. Okay, so you have on the left neurons start like in a sphere, and then they go converge into some very small number of neurons. Okay, and you see at the end the space of functions. The separator is very like piecewise linear because you select only a small number of neurons. Okay? It's just exhibiting the fact that the minimum norm interpolator has a lot of a few neurons which are active. And then final big one, comparing L1 and L2. So here on the left, this is L2, like smooth functions. On the right, this is potentially non-smooth functions. And you see here, happening at the end, when you learn, you end up with like non-smooth function on the right, and here it's a kernel method, hence you get smooth functions. This was the video. I won't show the other ones, but sorry about that. I'm happy to deserve my apéro. Well, yeah, like try adding I don't hear.
Yes, thank you so much, Francis. I think that we cannot have a Q&A right now because of the schedule, but we're going to ask you a lot of questions at 1 p.m. Oh, yeah.
Okay, very good.
Okay, thank you so much.
Excellent. Yeah, so it's my pleasure to introduce the next plenary talk. And of course, I'm delighted that the apéro of the previous speaker was indeed saved. That was great. So it's my pleasure to introduce the next plenary speaker of our joint Minds and Ideas Symposium. He's our own Professor Brice Menard. So he's on the faculty in physics and astronomy at Johns Hopkins. He received his doctorate from both the Institut d'Astrophysique in Paris and the Max Planck Institute in Astrophysics in Germany. He was a postdoc at the Institute for Advanced Study in Princeton before joining Hopkins. His research combines astrophysics and statistics. His work has led to the detection of gravitational magnification by dark matter around galaxies, a new way to automatically find trends in complex data sets, and many other contributions. He's a recipient of numerous recognitions, such as the Henri Chrétien Award by the American Astronomical Society. He was named the 2012 Outstanding Young Scientist here in Maryland, received a Packard Fellowship for Science and Engineering, and last year's Johns Hopkins President Frontier Award. So we're really delighted that he's joining us today to present the lecture entitled The Sequencer, How to Reveal the Main Trend in Your Data Set. And so, Brice, over to you.
Thank you, Charles. Let me share my screen. All right. Is this working well?
Yes, excellent.
Excellent. Okay. So yes, thank you so much for having me as a speaker here. I'm going to tell you about work we've done over the past couple of years, for which the goal is to extract the main trend in your data set, basically. So we just heard a talk about neural networks, and as we all know, they are very powerful. They can do all sorts of interesting things with data, but in order to use them, one needs to have training sets. And very often, when we do scientific exploration, we don't have access to these training sets. We don't yet know how to properly label the data, which features are interesting. So the mode in which we do exploration and leading to discovery potentially is different. And so I'm going to talk about this today. And so if we step back and look at the bigger picture in science and how we do science, in general, the key is to observe the world around us, which tends to be very complex. And we are going to collect data about the world. And we are going to look at this data to try to extract simplicity. Okay, so that's really the key process that we do as scientists. There's a beautiful quote by Gibbs, which summarizes this very well. And he's telling us that, you know, the principal object of research is to find the point of view from which the data appears with its greatest simplicity. And so what is very important to see here is that typically what we do, once we have data, we are going to look at data from different points of view in different ways and on different scales in order to look for something that's going to reveal simplicity. But this process, unfortunately, tends to be more of an art than a science. There is no guiding principle beyond this was on how to do this. So I'm going to tell you a bit more about this today. For many years, it's very important to emphasize that this process has been done through visual insight. Okay, people acquire data, they look at the data, and that visual insight is really the key that has allowed us to extract the simplicity for centuries. But things are changing now. So let me tell you a bit about this. Imagine you collect, you know, data for 20 objects. Those objects could be images, they could be spectra, audio recordings, they could be text. So you have these 20 objects. So usually one tries to organize these objects and look for structure. So this structure, for example, could be on the left, different clusters. If that's what we find in the data, we might label them type A, type B, type C, and then we start to understand something about the data. In other cases, we might find a continuous trend, which is what you see here in green. That's a one-dimensional trend, one-dimensional manifold, which sometimes we will call the sequence, a series, etc. And we can go to higher dimensional variations in 2D or in n dimensions. The key point here to realize that fundamentally data has shape, right? So we are seeing different shapes here when we simply try to organize the data. But what the key is that shape then has meaning, all right? So what we want to do in data analysis is really to try to get to the meaning of what the data has to tell us. And we can get to that meaning by trying to understand the shape of the data. As I said before, this has been done using visual insights for many years, many centuries actually. But things are changing. As our ability to collect data gets better and better, we tend to manipulate data sets that are richer and richer. And this is a real challenge because we can no longer explore most of the data that we have visually. Now we must explore the data mathematically. And this is very different. It's different for me because what I can do with my eyes and my brain is way more powerful than what I can do by manipulating equations. I wish my mathematical skills were as good as the combination of my eye and my brain, but that's not the case. So how to do that? So let's look at the process. Here is a data set. It's actually relevant. This is showing for 20 US counties, the positivity rate of COVID-19 from March to July. So it's a rather small data set and rather simple. We look at it, we can understand the main trends, and we can ask the question, can I reorganize the objects in my data set in some meaningful way? And I could, for example, if I have external information, I could reorganize this depending on population density. Okay, so if I do this, it's the same data, it's just reordered. And what I have now is that counties with high population densities are at the top and low population density at the bottom. And just by doing this, I can see that I start to see simplicity in this data set that is emerging. And there's basically a story emerging here at the same time, that in high density populations, then the propagation is going to happen more likely and earlier. So if I know this external information, I can reorganize my data and see simplicity. But we can flip this around. The question is, can I try to reorganize the data myself in order to get to that simplicity? And if so, then a story is going to emerge. And then from the shape of the data, I'm going to get some meaning potentially. So how can we do that? In this case, it's simple, but let's look at this more generically. So the key point is that if I can reorganize my data, if I can order it properly, that can reveal simplicity and meaning. Okay, so this was a simple data set. I can look at a data set that is a bit more complicated. This is a series of 20 timelines. And you might be able to say, yes, I can see a bump, I can look at the mean position or the peak of the bump, and I can reorganize the data according to this feature. And you would get something like that. And yes, this is going to tell you potentially an interesting story about the data. But let's continue. Let's look at this data set now. Okay, it's not very big, but it's more complex. In this case, I can no longer point to a specific peak to select to organize the data because it's more complex. However, this data is very simple. If I reorganize it this way, I see there's a very simple underlying trend in this data set. Okay. And I can go to even more complex data like this one. This is a case where I cannot even pay attention to specific features. This is too complex and too messy. However, again, there is a way to organize this data in a meaningful manner. So if I go across this complexity axis, what I see is that the more complex the data, the harder it gets to identify features, to come up with models and descriptions of the data that will allow me to organize it meaningfully. So how can we approach the problem generically? So this is work that we've done. This is in collaboration with Dalia Baron, who is a graduate student. And I'm going to give you the key idea of the algorithm that we developed in order to do this process. So we can start with some raw data that we have on the left here. Let's say I have about 20 objects in this data set. What I can do is to take all the pairs of objects, and each time I can measure some similarity between them. By doing so, I can create a graph of similarities. So in practice, this is done by computing an adjacency matrix for a given similarity measure, but I will not go into all these details right now. The idea is that I can, by linking all the pairs of objects and how similar they are, I can compute this graph. This graph is still a complicated beast. What I can do is to try to look at the core. I can try to simplify this graph as much as possible. I can look at its backbone, and this is called the minimum spanning tree, right? So I can compute the minimum spanning tree, and what that is a way to connect all the points in this graph, trying to minimize the total distance between the points. Okay, so this is very well defined mathematically. And once I have this minimum spanning tree, I can look at it and I can look at its shape. Again, the shape of this minimum spanning tree is something we can define mathematically very well. And I will not go into the details, but I'm just going to say, okay, let's just draw a contour around it and look at this shape. In this case, for this graph, there is no preferred orientation, direction, and shape. It looks very roundish, all right? So that's what we can see for this data set. And in this case, I cannot say much more about the data. However, if I take a different example, all right, I have a new data set on the left, I'm going to redo the same process. I compute a graph of similarities. I look at the backbone of this graph, but in this case, what I find is that the minimum spanning tree is very elongated. There is some precious shape information in this case. If I draw a contour around it, if I measure its ellipticity or its elongation, I find something that is stretched in one direction. And this is telling me that there is something fundamental in this data set. There is some ordering of the data that is special. And now what I can do, I can march along all the objects of the data given by this graph, and I can reorder the data that way. And in many cases, by doing so, I'm going to find something simple, and often meaning is going to emerge out of this process. So the key point here is that if I compare the raw data on the left and the order data on the right, now the y-axis in the vertical direction now is telling us a story. And often the y-axis means something. All right, so this is the key idea behind the algorithm we developed. I'm going to tell you just a little bit more about it in practice. If you remember, how we started, and what Gibbs is telling us is that what we want is to find a point of view from which the data is going to appear simple. So in practice, what we do, we are going to look at the data on many scales, and we are going to use many different types of similarity measures. So we are going to compute lots of graphs. And for all these graphs, so these graphs will allow us to look at the data from these different points of view. What we can do then is to look at their backbones, their minimum spanning trees, and we are going to look at their shapes. And usually, often, we will find one way to look at the data that is going to lead to a very elongated minimum spanning tree. And in this case, we know that there is a very special ordering in the data. We can follow it, we can look at the data again, and we can see some meaning in the data set. So let's see how it works. We can start with a simulated data set. So on the left, I have about 10 objects, all right? So 10 vectors or 10 functions. And what I have next to it is a bigger data set. Now I have hundreds of them, but because I have hundreds of them, I can no longer plot all these curves on top of each other. So I'm going to use a heat map instead. So you can consider the one on the very left to be 10 examples of the data set that I have in the middle. So this is the raw data. And what I can do, I can run that through the sequencer algorithm that I just introduced and see what I get. And by looking at the data from all these different points of view, the algorithm is capable on its own to find a reordering of the data that allows us to see simplicity in it. And this was indeed, what you see on the right is how the simulated data set was designed with this W-shaped feature on small scale, and the algorithm is capable of finding that on its own. Right? So this is an example with simulated data. We can look at now real data. This is astronomical data. So what we have here is a collection of spectra. On the left, we have about 10 of them. And next to it, we have a collection of almost 1,000 spectra. So this is now a much bigger data set. And same thing, we can look at this. And the question is, is there some simplicity behind this? What is the data telling us? We can pass this through the sequencer to simply reorder the data. So again, there is no manipulation. I'm not stretching anything. I'm just reordering all the objects in the data set. And what the sequencer can do is to give us this as an output. And what we see here is that this data set is actually quite simple. And if I move from the bottom to the top, I can see that all the objects are very similar. It seems that as we go through this sequence, they are shifted a little bit to the right. And indeed, if we look at the physics, what we are seeing here are different quasar spectra that are redshifted, okay, due to the expansion of the universe. And so the objects that are at the top, they are very far away from us, very significant redshift effect. And at the bottom, they are very close to us. And I've been able to get to that point without any physics, without any data analysis, without anything, without knowing anything about the data. This simple reordering of the data that I can do in a very natural way by using shape information leads me directly to a point where I can start to look at the data and ask physical questions about it. So this is, I think, very interesting. We can look at more complex data sets. This is now another data set with several hundreds of objects in it. If we look at it, 10 examples on the left and several hundreds on the right, it looks very complex, and I would not know how to compute a model or select a feature to reorganize this data set. But let's pass it through the sequencer and let's see what the sequencer finds. This is what we get, right? Quite remarkable, right? This is a very high level of complexity. The algorithm doesn't know anything about the data, and it's understood that by reorganizing all these rows, one can actually create an ordered data set that has clear meaning to us. All right, so I think this is very interesting. It can be very useful to many people like you in your scientific research, whether you have data in biology, in chemistry, in social sciences, in any domain. We all try to find this simplicity in the data to understand meaning. And this is something that the sequencer algorithm can help us to do. So we can go back to all sorts of data sets, as I showed, simple data sets. We can, with the same algorithm, reorder them meaningfully. Those are small data sets with dozens of objects. We can run on hundreds and thousands and more objects. So this is another list of examples where each time the same algorithm is capable of finding a meaningful way to reorder the data. So for this to be useful to you, we've created an online interface. This has been done with Manu at Hopkins, and it's been supported by IDIES. We're using some of the IDIES infrastructure to run the website. So I encourage all of you to go and use it. I think it can be very interesting, very useful in your data, in your research, potentially. You can go and to the website, you can simply upload your data set. The algorithm will run for you and will show you the best ordering that it can find. And this ordering might very well be extremely interesting to you. The code is publicly available. You can also run it on your own. It's available on GitHub. So now in the minutes that I have, let me tell you about some discoveries that have been made with the sequencer algorithm. The first one is by us directly in astronomy. So when you look out there in space, you find lots of galaxies. We can take pictures of these galaxies, like the one you see, and we can take spectra. And the spectra will tell us about the chemical composition of the system and so on, as well as information about dynamics, etc. A very rich type of information. Many galaxies out there now, we know, have a very massive black hole at their center. Okay, this is a black hole that is heavier than 1 million times the mass of the sun. And astronomers are very interested in understanding this system. So we can probe these black holes through the spectra that you see on the left. So what we did here, something extremely simple. We took about 2,000 spectra from the Sloan Digital Sky Survey, and this is shown here as the heat map. So every row of this image at the top is a spectrum. And we ran that through the sequencer. And the sequencer showed us a beautiful trend. And what is amazing here is that this data set has been public for about 20 years. It's been studied by hundreds of astrophysicists. And this trend has been completely missed by the community. The trend that the sequencer found, can be expressed now in some more physical ways, and I will not enter into all the details of this analysis. But what was very exciting to us is that by trying to understand this trend, we found a new way to estimate the mass of these black holes that are at the center of galaxies. And so this is a very exciting result, completely unexpected. And the reason is that most of the time, scientists look at the data and they try to look for what they expect. And this is one of the cases of something that was not necessarily expected. People did not look for that, and therefore they did not find it. Okay, and the beauty of the sequencer algorithm is this ability to go blindly and just look for simplicity in the data without any assumption. So now I'm going to show you another example. This time, this is outside of astronomy. It's in geology and more specifically in seismology. So all across the US, there are stations that are recording the vibrations of the Earth, seismometers. When an earthquake happens somewhere around the world, it's going to propagate a wave that will cross the US, and the vibrations are going to be recorded by these thousands of seismometers. So this is generating a lot of data because they are constantly, low magnitude earthquakes, and seismologists are trying to make sense out of this data set. So I'm going to show you one example here. Again, it was quite surprising. So what we did, so seismologists have access to many thousands of these seismograms, and they try to find correlations in structure in those. We did a number of tests with the sequencer, and we just uploaded data for a special type of wave, and this is a seismic wave that basically goes very deep inside the Earth and bounces back onto the liquid iron core that is at the center of the Earth, comes back to us. And what happens is that sometimes we hear or we detect the vibration, but then a bit later there's an echo, there's another one that is coming. And seismologists knew about this, but did not really pay attention or try to understand if there is interesting information from this. So what we did here is an example where we used 6,000 seismograms. And again, I will not go into the technical details, but this was shocking to us. We basically found that, or the sequencer found, because the algorithm made the discovery, not us, that there is actually a very simple structure if we look at these echoes, those waves that come with a little time delay. And by trying to then understand what this is telling us, we had a very simple trend in the data that again had been missed by most of the community. We were able to access very precious information that allowed us to make a map of structure deep inside the Earth. So we are at depth of about 3,000 kilometers here. And this is what you see on the right. So by combining these seismograms from many stations across the US, and by basically listening to earthquakes that are coming from Asia, we were able to have some coverage of the inside of the Earth, which is below underneath the Pacific. And making use of that new trend that was found by the sequencer, we now have access to a new type of information that's extremely interesting. And we were able to reveal that we find some very dense structures deep inside the Earth, which happen to be located underneath groups of volcanic islands like Hawaii and the Marquesas Islands. So again, a beautiful example of a discovery that is made in a context where we don't know what to look for. All right. So that's why I believe that this approach can be very powerful for scientific discovery in general, and I hope it's going to be useful to you. And I encourage you to use the sequencer algorithm. So now let me just summarize everything I've said. Let's step back again and remember that as scientists, what we are trying to do is to look at the world around us that is often complex, and we're trying to extract this simplicity. And I hope I have convinced you that data has shape and shape has meaning. And so if we follow that route, we can actually extract, we can find trends in data, and we can extract meaning out of data set in a very powerful way. The algorithm is available online, so you can simply upload your data sets and see what the algorithm can find for you. You can also download the code and run it yourself if you like. So I do encourage you to use it. And if you need help, feel free to reach out, and we will be happy to help. All right, I'm going to stop here and thank everyone for your attention.
Thank you so much, Brice. Wonderful talk, very impressive results. Since we're a little short on time, I'm not going to ask and have answers to questions, but to encourage people to go to one of the breakout sessions over the lunch break. Very briefly, one question from Thomas Bertaland, which maybe you can talk about over the lunch break, is, have you compared this approach to other techniques, kernel-based or diffusion maps on similar data? And then I guess Nandan Kulkarni is remarking that this is like the super sonar application. So very interesting. Thank you again, Brice. And I think now we proceed to the next presentation. The next talk is a 15-minute, the second Seed Award update we are hearing from today. It's by Dr. Neil Paliwal from Johns Hopkins. And so this project and the talk are entitled An Artificial Intelligence Approach Towards Predicting Recurrence of Atrial Fibrillation in Patients Undergoing Pulmonary Vein Isolation. So Nick, I hand it over to you. Let's hope the screen sharing will work. Excellent. So far, so good. Very good. And full screen, and off you go.
Thank you so much for the introduction. So I'm a postdoc in the Alliance for Cardiovascular Diagnostic and Treatment Innovation at Johns Hopkins. The PI for this project is Dr. Natalia Trayanova, and the co-I is Dr. David Sprague, who is in the Division of Cardiology at the Johns Hopkins Hospital. So this work is a lot of other people have also contributed to this work. I just want to name them out here. Julie Shade, Rebecca Yu, Dr. Ida Ali, and Dr. Pallavi Pandey. So now I'm just going to talk about how we are using artificial intelligence and the clinical data to help improve the clinical management of patients that have atrial fibrillation. So just quickly about atrial fibrillation, it is the most common form of cardiac arrhythmia where the heart rhythm is irregular. So if you have a regular heart, the impulse comes from the right atrium and goes through the left atrium and through the ventricles, and the heart is beating properly. However, in atrial fibrillation patients, there are abnormal impulses in these atria, that is the upper chamber of the heart. And because of that, these patients are at a high risk of stroke and have a high morbidity and mortality. And it has also been estimated that the prevalence of atrial fibrillation is going to increase in the next few years and is going to have a huge burden on the healthcare system of the United States. In terms of treating patients that have atrial fibrillation, pulmonary vein isolation is the standard of care right now, where the cardiologist would insert a catheter into the left atrium of the patient and kind of ablate or burn off tissue around these 4 veins that are supplying blood to the left atrium. So these 4 veins are called pulmonary veins. And once you see this red kind of circling around these 4 veins that are supplying the blood, and this is called the pulmonary vein isolation, where you are just trying to burn the tissue around the veins to to stop those random triggers of atrial fibrillation. However, in the current clinical practice, around 50 to 60% of patients that undergo this PVI procedure recur. So the procedure, so the patients have to come back and get treated again. Now, the consequence of this AF recurrence after treatment is that additional procedures pose high increased risk because of the because these patients are undergoing these additional procedures, and also it increases the financial cost of the whole procedure, putting the financial burden on the healthcare system. So in order to try to address this issue, the goal of our project is to develop a data-driven tool that can help the clinicians in identifying which patients will have successful PVI and which patient might not, so that they can manage the patient that might not have successful PVI differently. I just want to first put out what's the kind of data that we are dealing with here right now. So first thing, for these patients, we have the clinical data. We have the base demographic of the patient, age, sex, race, and all those information. We also have the clinical information about the patients, if they had a heart failure or a stroke or hypertension. And we also have some clinical measurements of the left atrium, which are done prior to the procedure. Apart from the clinical data, we have the medical imaging data, which is kind of a part of the clinical data because this is required to guide the actual PVI procedure. So in terms of this medical imaging data, there are two main types of data available for left atrium, which is a cardiac computed tomography image, cardiac CT image, and the late gadolinium enhanced MRI image. Cardiac CT image provides the structure of the left atrium. The LGE MRI is a more specialized form of imaging where you can also look at the substrate in the wall of the left atrium, and it's very useful actually for doing virtual heart simulations that we do at our center. So we have been working on these virtual heart simulations to identify the AF inducibility in the patients using these LGE MRI images. So we have done a lot of work in this in the past number of years, and this is also kind of data that we have at our center. So this is the three main types of data that we have available to really try to address the issue of recurrence after PVI. So our approach is to use a combination or collection of these data and use artificial intelligence to develop models that can predict the success or failure of the PVI. So the idea is, if we have some sort of a tool ready, if a new patient with AF comes in, we can extract the image-based feature from the clinical imaging of the data. We have the clinical features that are the clinical documented features for the patient. And we have the simulation features that we run, and then use some sort of a classification model that can tell us whether this patient will recur or not in terms of AF after the PVI. The approach we are taking here is use the already available data of retrospective AF patients and then try to develop these tools. So we have the two kinds of data available, the clinical data and the imaging data. With the imaging data, we propose to use deep learning to get accurate left atrium segmentation, accurate and efficient left atrium segmentation. And then using the same imaging data, we are also going to do the virtual heart simulations to get more mechanistic or information out of this, out of the left atrium. And then we plan to use the clinical data, the left atrium measurement data, and the virtual heart simulation data, and put it in a machine learning classifier algorithm, and then train a predictive model. Because we already have the outcome of these patients, it becomes more straightforward to really train these classifiers. Like I mentioned, we already have virtual heart simulations like models developed in our lab. It's quite advanced. And the motivation behind it is that the basic clinical and image-based features do not really give us any mechanistic insight on the underlying AF induction, how it propagates throughout the left atrium. So we have done these computational modeling where we do a multi-scale physics models from tissues level to cell level to really understand the electrical functions for each individual personalized left atrium model. So this is the pipeline that we use. We have the MRI images, and then we segment the images, and we get the 3D reconstruction. In this 3D reconstruction, like I mentioned, in the MRI images, we have the fibrotic and non-fibrotic substrate. The fibrotic substrate it's like it kind of shows like the scar. You can think about it like the scar in the left atrium. So it is important to have this fibrotic substrate because it really it has been shown that the amount and the distribution of this fibrosis really is responsible for these AF triggers. And then we do the personalized simulations. Now, before like developing this tool, there were some questions that needed to be addressed. The first question is, it has not been shown that clinical imaging and simulations can predict the recurrence after PVI. So that's one question. And the second question was, we already have these clinically documented parameters. Can we just use those alone and predict the recurrence? So we tried to address these two questions first before developing our tool. So let's first look at the question about clinical imaging and simulation. So this is the work done by Julie Shade in our lab. She has done amazing work in terms of using the imaging and simulation-based features and machine learning to predict the recurrence. So the pipeline is again the same. We have the MRI images, we get the imaging features, we get the simulation features, put it through a machine learning classifier, and then predict the recurrence of AF. In this study, we used 32 patients that had AF. They underwent pulmonary vein isolation. 12 of these 32 patients had recurrence after within a year. So we got the pre-procedural LG MRI images of the patient. We constructed the 3D models from the LG MRI and performed the simulation. And based on these simulation and image-based parameter, we trained machine learning models using 10-fold nested cross-validation. An important thing to note here is that there was no significant difference between the patients who did or did not experience AF recurrence in terms of clinical characteristics alone. So clinical characteristics were not able to predict whether the patient will have recurrence or not. I'll just quickly jump on to the results. Here you can see the ROC curve in the training, validation, and testing. And if you look closely, I is the imaging features and SIM-AF is our virtual heart simulation-based feature. And you can see in all training, validation, and testing, if you have both imaging and simulation feature, you get an AUC of 90. But if you have simulation feature alone, you get an AUC of 94. But imaging alone is lower than both. Same thing as we find in the validation as well as testing. So this kind of demonstrates as a proof of concept that simulation-based features are really important to make accurate recurrence predictions. And also, if you get rid of the imaging features, they kind of get assimilated in the simulation features. So we can also use the simulation features to have accurate predictions. Now moving on to the second study, that's something that we are currently working on. Let's just say take only the clinically documented parameters and see how good they perform in predicting AF recurrence outcomes. So we had 136 patients and 50 of them had recurrence after PVI, 80 were free from AF after PVI, and we had the following continuous features. So we had the age, sex, race, height, weight, and BMI. These were the patient characteristic. And then we had the left atrial diameter, left ventricular ejection fraction, and left atrium volume. These are clinically measured variables. And then we used 4 kind of classification algorithms: support vector machine, logistic regression, k nearest neighbor, and decision tree. And then we trained each algorithm with this kind of data with 5-fold cross-validation to do hyperparameter optimization. And the results did not show a very good accuracy in predicting the outcome. So we first we first did only the patient demographic data, and the highest accuracy was K nearest neighbor with 64.7%. Then we only used the clinical LA measurement, left atrial measurements, and the highest accuracy was 63.2. And if we combine both of these features, the best accuracy we got was 64.7. Now, I just want to point out here, these are like preliminary results. We are trying to optimize our models further, but from just preliminary data analysis, we feel like clinical factors alone might not be enough to accurately predict AF recurrence outcomes. Now, coming back to our tool, we are also parallelly working on developing the deep learning algorithm for automated segmentation. So the motivation was that because the current segmentation methods are very tedious and time consuming, and because they are fraught with error due to inter-user and inter-user variability, we wanted to come up with some sort of a automated approach that can do it quickly and accurately. So this work has been done by BME undergrad Rebecca Yu and led by research scientist in our lab, Dr. Rida Ali. So just a brief overview of the neural network. We first do the ROI identification, where we narrow down to the region of interest of the left and right atrium. So this is also done using a neural network. And once we have this ROI, we then do the segmentation prediction. A very good feature of our neural network is that we have a modified loss function which takes into account the actual anatomy of the left and right atrium. So we had 143 cardiac images for training this model. 86 were LG-MRI and 57 CTs, and these are the results. Like I mentioned, we have a new loss function which is based on the anatomy, and we found that if we use that modified loss function, we have higher dice coefficient and better performance. So this is kind of still an ongoing work, but we have been successful in developing this automated segmentation tool. And it's very important to have this, because if we have some sort of automated segmentation tool, we can do more accurate left atrial measurements, because the clinical measurements, as we have noted, are not that accurate because different users are calculating it using different ways. So this will kind of standardize the whole measurement for the left atrium and have more clean and objective data. So I just want to conclude is that we developed a data-driven approach to predict AF recurrence after PVI, which we believe is going to help massively in the clinical management of these patients. We also found that simulation-based features from our virtual heart technology have very high prediction accuracy, and clinical features alone were not able to predict recurrence after PVI with that much accuracy. And we also showed our deep learning-based automated segmentation technique that we have developed, and which is very fast and accurate. And in future, what we're trying to do is then combine all the clinical features, simulation features, and the geometrical-based features, and then identify an optimum combination of these features, which is able to give the highest prediction accuracy, and that can be translated into a clinical tool in the future. And I would just like to acknowledge funding from the IDIES from the seed fund grant, and Marcy to provide computational resources for a study. Thank you for your attention. And if there's time for a question, I'll be happy to take one.
Thank you very much, Nikhil. Yeah, so any questions we'll probably do later in the breakout sessions. Right now, I think we're running a little late. So let me thank you again for the update. Very interesting. And
thank you so much.
This point, we are going to the next segment, which are the poster madness session. And I'm handing it over to Tara, who I believe will direct the traffic for the posters.
Yes, and I'm actually going to hand it over to Eric, who's going to introduce our poster session and announce our winner. So Eric, go ahead and take it away.
Great, thanks, Sarah. Can you hear me?
Yes.
Yes, okay, good. So it's my pleasure to introduce the poster session for the 2020 Symposium. So this session is a way to foster and showcase collaboration between ideas and minds, and in particular students and postdocs. So in this year, we have 10 posters, and they cover a range of topics from astronomy, material science, the impact of COVID-19, among others. And many have utilized machine learning techniques in their analysis as well. Of those 10, 6 opted to take part in our competition, where we had judges judge the posters on their merit, their scientific content, visual presentation, and they had access to the posters in isolation. And in addition to the glory, that stakes is also a $50 Amazon gift card. And while I'm pretty sure the judges enjoyed perusing all of the posters, there could really be only one winner. And drum roll, please, all up in the envelope. That winner this year is Vedant Chandra for the poster Hunting for Metal-Poor Main Sequence Stars in SDSS. And when you see it, I think you'll agree that this poster had really clear and concise descriptions of the goals, methods, and results. And I think in particular, the figures and text really worked well together to tell the story. So I hope you'll join me in congratulating Vedant Chandra for the win. And without further ado, each author from now will give a couple-minute introduction to their poster with a slide. And please take the opportunity to join any posters you're interested in further chat with in the breakout sessions. I believe the Zoom rooms are listed in the detailed agenda you got emailed earlier. So I'll hand it back to Tara to go through the slides. Thank you very much.
Great, thanks so much, Eric. Yep, we're going to jump right into it. So I'll share my screen and Carey is going to kick us off. All right, there you go.
Okay, hi, I'm Carey Fibrillation. I'm a graduate student in the Department of Physics and Astronomy here at Johns Hopkins. I'm going to talk to you today very briefly about a project my group and I have been working on. So the problem we're trying to solve involves selecting members of dwarf galaxies. So we have a bunch of data in the direction of different dwarf galaxies around the Milky Way. And this data contains stars that are both from the dwarf galaxy and from the Milky Way. And we want to disentangle these two populations. And we decided to do this by assigning membership probabilities. And we use a hierarchical Bayesian mixture model framework. However, actually calculating the probability that a star is a member of a dwarf galaxy is super difficult. So we use Markov chain Monte Carlo techniques to sample the distribution and get a nice posterior distribution of our data. The general framework is we model our data as a mixture of populations, the Milky Way and the dwarf galaxy. We use information from the literature to determine the distributions of the physical parameters like age and stellar masses for our data. We then sample these distributions and use stellar evolution models to turn these physical parameters into observational parameters like brightness. We repeatedly simulate our data and compare our synthetic observations to our real observations and evaluate the likelihood. We do this a bunch of times and we end up getting the posterior distributions for all of the physical parameters, as well as probability of membership for each star in our sample. This is computationally expensive. We are fitting tens to hundreds of thousands of stars in each field. So we use a GPU to accelerate the fitting process. We developed this technique for the prime focus vector graph, which you will hear a bit more about later today from Laszlo de Bosch. But we will make this software open use, and we believe that there's a lot of great applications for other astronomers out there. I think my 2 minutes is up, so thank you.
Great, thanks so much, Carey. Next we have Zuru. There you go.
Oh, there we go. Awesome. All right. So hi all, I'm an undergraduate BME student, and great thanks to IDIES for supporting my project over the summer. So when I was working first in the ED, I noticed that many physicians were not following the clinical pathways that is often recommended by the hospital. Over time, one of the common complaints that came up was that these pathways did not simplify the diagnosis process by much and were considered far more restrictive than need be for the benefit that they did provide. So one of the biggest issues with this is that these pathways either were considered too vague in order to cover the many disease presentations, or too specific and not covering enough of these presentations. Of course, this makes sense that the companies making these are not making something that is specific to a region or time. In other words, they're creating a very inflexible kind of software that has presets that does not take into account the local influence such as diet and pollution that can change, for example, how these diseases show up in the clinic. And so my solution here, of course, is to try and apply some machine learning to simple patient vitals in order to supplement physician decision-making with self-updating predictors for certain diseases. And overall, I chose pulmonary diseases to start off with because in the MIMIC3 data set that I used, it is very common. And I can easily understand as an undergrad what some of the parameters that I could start out looking at for exploratory data analysis. It wasn't too overwhelming for me, at least. So after some fitting of a gradient boosting algorithm, I found a satisfactory accuracy about 80%. Of course, taking into account the chosen parameters such as oxygen saturation, breath rate, stuff like that. There are, however, some pretty big limitations to what I have done here. The biggest is, of course, that extrapolation that I needed to do in order to fill in all the gaps in the available MIMIC3 data set. And similar, kind of following onto that problem, with the amount of data extrapolation I did, the final result of the data was kind of muddy to the point to where I can't distinguish very well between the different types of pulmonary diseases. For example, I can't distinguish COPD from pneumonia, something like that. Hopefully these issues can be solved in future study and maybe in a clinical setting by just constantly feeding necessary data that we know are good parameters into the program. The ability of the program to update and improve itself upon its newly available data should make it very flexible and applicable and improve upon itself with more time that it is used. And that is the whole reason why I chose it after all. And thank you. That I'll be saying for the 2 minutes.
All right, thanks so much, Zero. Up next, we have Nick Carey.
Hi, my name is Nick Carey. I'm a very recent computer science PhD graduate. And this is one of my recent projects where we apply image object recognition towards a user feedback system for stable crystal growth in a floating zone furnace. This is down in the Paradigm Lab in the basement of Bloomberg. It was a fairly straightforward application of image segmentation, and we find some interesting trends in the classification of about 1 million images of previous crystal growths that I'll discuss. And if you're interested in applying image classification or object recognition to automate a process or discover visual trends in your lab, come on by to the poster room and I'll be happy to discuss applications, maybe a job.
All right, thanks, Nick. Up next, we have Coco Kai and Matthew Zhao. There you go, guys.
Hey guys, my name is Coco Kai. I'm currently a senior AMS major at Hopkins.
Hey everyone, I'm Matt and I'm a current junior studying BME and AMS at Hopkins.
So Matt and I started this project with COVID-19 back in this past summer with our faculty sponsors, Dr. Tomas Budavari, Dr. Jackie Jennings, and Dr. Jim Liu. We started this project by asking ourselves 2 important questions. First of all, how has COVID-19 affected population movement patterns? And do those patterns have anything to say about the spread of this disease? And secondly, what are the differential effects of social distancing on mobility and COVID-19 by high minority, high essential service, and regions with other high-risk populations?
And so in order to address these 2 questions, there were 2 primary data sets that we looked at. One of them is the 2017 ACS census data set, and the other is one provided by Physical Labs, which details geolocation data for more than 11 million user IDs, unique user IDs in the Maryland area between the months of January and July 2020. So a lot of the processing that we used to handle this data was done in SciServer using Python or PySpark. And what I wanted to do was extract a lot of summaries for population movement from the geolocation data. So things like how far people are traveling day to day, and also where they're traveling to and how long they stay in those areas.
So for the census data, I used the 2017 ACS 5-year survey using the census API in Python. I customized the data field of interest, including various socioeconomic measures, as well as occupation and transportation information. So by the end of the summer, Matt and I were able to combine the two data sets at the same unit of aggregation at a zip code level into a master data frame and perform some preliminary data analysis.
All right, thank you both. Up next, we have Vedant Chandra, who was our poster competition winner.
Thank you. Good afternoon. I'm Vedant
forward,
Chandra. Sorry. All right. So I'm Vedant Chandra, and I'm a senior in the Department of Physics and Astronomy. This summer, I was gratefully supported by the IDEAS Summer Student Fellowship to work from India with Professor Kevin Schlafman from our department on the project Hunting for Metal Poor Main Sequence Stars in the Sloan Digital Sky Survey. Some of the oldest stars in the universe were formed soon after the Big Bang in an environment where nearly zero metals were present. Indeed, these stars themselves formed the first metals. The best way to search for such metal-poor stars is in large spectroscopic surveys like SDSS. But there's a big problem. As you can see in this figure, the spectra of metal-poor main sequence stars look almost exactly like the spectra of a far more common type of star, white dwarfs. Previously, people have tried to visually distinguish them, but that's prone to human error and completely infeasible for larger surveys. So this summer, we developed an automated algorithm that takes in spectroscopic observations like the ones you see here and classifies them as belonging to a white dwarf star or a metal-poor main sequence star. We validated our classifier on existing data from SDSS that had reliable classifications, and we found it to be both accurate and precise. We also found numerous new and interesting metal-poor candidates and also rediscovered dozens of known extremely metal-poor stars, which demonstrates that our search technique is effective. Our work is currently undergoing peer review at the Astronomical Journal, and I'm happy to share a preprint with anyone who's interested. In the future, we will apply our techniques to upcoming large-scale surveys like SDSS-5 and DESI, and potentially find tens of thousands of more extremely metal-poor candidate stars. This massive data set will enable us and the research community to trace the chemical history of the Milky Way and probe the formation and history of the very first primordial stars in the universe. And so once again, I'd just like to thank IDEAS for supporting this research and for the gracious award today. And thank you for your time.
Great, thanks so much, Vedant. Up next, we have Gina Elnasar.
Hi, everyone. My name is Gina. I'm an undergraduate senior in computer science and biophysics, and I am currently a student in Dr. Barrick's lab in the Department of Biophysics. Our lab looks at the protein stability, and our belief is that a protein sequence, its primary sequence, is amino acid sequence, its statistics of that sequence has key information that could be a key predictor in the Gibbs free energy or the stability of the protein. So given that we don't have access to I don't have access to doing experiments right now, I decided to take a approach using statistics and machine learning to see whether or not the statistical information embedded within a primary sequence of a protein would be an accurate predictor of the Gibbs free energy. And it turns out that we can get 70% accuracy at predicting whether or not a protein is stable or not stable, just using the statistics and very, very rudimentary structural information. So I'll be happy to discuss that and our methods in the breakout session.
Thanks, Gina. Up next, we have Peter Gu.
Hi, I'm Peter Gu. I'm a grad student working under Professor Tomasz Budovari. I'll be talking about our method for a scalable algorithm for mass viewshed calculation. So viewshed is a set of terrain locations that are within line of sight of an observer. And this is a process that's easily calculated with a GPU in parallel. But our goal is to calculate many viewsheds also in parallel. So the key to this is that we stream the terrain data, which is usually LiDAR, into the calculator, and then iterate over many tiles over all the viewsheds in parallel. So if you look at the cross-section picture, you can see how a viewshed works you have an observer, and then you have points that are either in line of sight or not in line of sight. And the difference is that for points that are not in line of sight, there's actually a slope between the observer and the point on the terrain that is less than the slope of any point that's closer than that point. Whereas if something is in line of sight, it has the highest slope encountered so far. So calculating these slopes between observers and the ground is very important. So the algorithm works like this. There are square tiles in the terrain data, and for each tile, we calculate the maximum slope for all the rays emanating from the observer outwards to its maximum range. So that's step one. Then step two is to iterate over all the tiles and observers and remap the data so that each tile contains the highest slopes encountered so far. And then in step three, using that data, the tiles have knowledge of the highest slopes encountered so far. So the viewshed sections within that tile for every observer can be completed and then combined at the end. So you can see there's a picture of a viewshed. And the bulk of this work is actually implementing this calculator with CUDA C++. And the way that this works is that we load the terrain data in and out of the GPU because the terrain tiles are set up to fit just one tile in the memory. And then all the rays for all the observers are handled in parallel because each one is given a separate thread. And so we implemented this, even with a laptop, it's able to process many viewsheds with a large size pretty well. With a desktop, we're able to calculate hundreds of viewsheds with ranges of about like 20 kilometers. And there's always room for improvement to basically organize the code better for the GPU hardware or scale up the GPU hardware. And also we'd like to use this to basically optimize the locations of many observers. So you can imagine like a search and rescue type of situation where you have a plane that flies around. It has many different locations and you want to find the line of sight. Yeah.
All right, thanks, Peter. Up next, we have Brian Brohl.
Hello, everyone. My name is Brian Brolin. I'm a research scientist at Vanderbilt who's collaborating with Tomasz as well as a few others here from Johns Hopkins. Today I'm presenting some of the work that I've been doing recently, focusing on making deep learning more accessible to people in the natural sciences. In particular, I'm going to be focusing on an integration with SciServer, of which you guys should be pretty familiar, so I won't spend a whole lot of time explaining that part. Now, one of these, so one of the projects that I've been working on here in trying to make, or one of the efforts in trying to make deep learning more accessible has been through an environment called DeepForge. Now, DeepForge, I apologize for the small text, and I was hoping I could zoom and move around a little bit, but anyway, in the left panel here, I'm talking about DeepForge. It's a machine learning gateway designed to make deep learning more accessible, and it tries to emphasize on three main fronts: productivity, reproducibility, and extensibility. So on the first of these, when we start looking at things like productivity, and kind of a little bit of accessibility, this includes like a visual editor to create neural network architectures. Now, the useful thing here in particular is like each layer, if you have any questions about what it does, and it supports all the layers in Keras right now. It has a little help icon that'll include information about every argument, as well as links to papers where these layers were first introduced. It also includes, as you can see in the little figure here, information about like shape information, or the shape of the data, or the tensors as they're flowing through the network, and design time error detection and things like that. So the real focus here is trying to let people focus hopefully on the content and less on the tooling around it. There are other little affordances like collaborative editing support and integrated version control and things like that. But oh my goodness, I apologize. My timer screen went off and then I realized that I just hit time. So I'm going to try to wrap this up pretty quick, but we also focus on things like reproducibility with automatic version control and capturing data provenance. So given a piece, like a generated artifact, we can reconstruct a pipeline that would create it. And of course, so this is the publicly available machine learning gateway, but we don't want to try to migrate people away from their existing like data stores and compute resources. So what I wanted to focus on here was that one of our recent developments have been integrating with SciServer. So right now there's a public deployment of DeepForge, where if you want to use your data from SciServer or SciServer compute to actually execute the jobs, you can design the problem and work on solving the task within DeepForge, but leveraging your existing HPC infrastructure. Anyway, I'm significantly over time, I think. So if you have any interest or have any questions, feel free to reach me at the breakout room.
Great, thanks so much, Brian. And last but certainly not least, we have Ambar Paul. Here we go.
All right. Hi, I'm Ambar. I'm a PhD student in the CS department advised by René Vidal. I'm going to talk about attacks and defenses on AI systems. So in the top panel on the left, there's an image of a running dog. State-of-the-art deep learning-based classifiers are able to classify this image correctly as being that of a dog. However, if you add a small imperceptible perturbation, as shown in the middle of the top panel, this slightly perturbed image is now classified as a cat by the same deep learning classifier. This is weird, and such algorithms that are used to produce these small imperceptible perturbations are called adversarial attack algorithms. Now on the bottom panel, we now have the same perturbed image that was there that was produced on the top panel, on the right of the top panel, and now we smooth it to produce a corrected image on the bottom right. This smoothed image is now classified correctly to be the original class, which was dog initially. This algorithm is called an adversarial defense algorithm. Now in the machine learning community recently, there has been a cat and mouse game between these attackers and these defenders, where new attacks are proposed, which are then sort of mitigated by new defenses. And these defenses are then again broken by new attacks, and this cycle sort of continues. In this work, we provide this rigorous theoretical method to end this arms race for one particular family of classifiers, essentially using tools from game theory. The main result is to show that a particular attack algorithm, which is called the fast gradient method, and a particular defense algorithm, which is called the randomized smoothing method, they are optimal in this setting. That is, you cannot do better than attacking with FGM, and you cannot do better than defending with randomized smoothing. And the way they are optimal in a game theoretic sense is that they form a Nash equilibrium. I welcome everyone to check out more details at our poster and as well as our paper at NeurIPS 20. Thanks a lot.
All right, thank you so much, and thank you to all of our poster participants. We really enjoy hearing about your work and everything you've been working on. So with that closes out our morning session. Thank you to everyone for hanging on. We'll be back at 1:30 to kick off the afternoon. Don't forget to stop in at those poster breakout sessions. And then there is the breakout session with Francis Bach starting at 1, I believe. And yeah, there's also a couple breakout rooms if you just want to jump in and kind of talk and network with anyone else attending today. So thank you so much, and we'll see you back this afternoon.